In this lesson, we're going to take a look at how to deal with vectors and Coulombs law. So force, of course, is a vector. And if the vectors are not along the coordinate axes, we're going to have to resolve them into components, add them. Find net force on the positive 2 microcoulomb charge. All right, so as we scan the situation, we should see that these are going to repel each other. And so we're going to see a force this way by the positive 4 microcoulomb charge. And then here it's going to be an attraction, so we're going to see a force that's up this way. It's a bigger charge, but it's also a bigger distance. And so this would be a force by the -6 microcoulomb charge. Okay. So in a situation like this, I highly recommend staying organized. And so I coach my students to make a table and break up the forces into their X components and their Y components. Okay, and then we'll list each force and then we'll do the X and Y components. So we'll break up the force starting here by the +4 microcoulomb charge. And then we'll also put an entry for the force that's caused by the -6 microcoulomb charge, and we'll put that here. All right, so let's just kind of lightly here. So the X component, well, we don't really have to do any math for this first one. Well, I guess we do have math, but we don't have to do X and Y components. Excuse me, because this is only along X, and none of it is along Y. So now we can go ahead and do Coulomb's law. So I'll use the constant K, and then it's going to be 4 microcoulombs times 2 microcoulombs divided by the distance squared. And so that's 7.2. And positive 7.2 because it's along the positive x-axis. Now for the -6, let's recall what we just did. And again, we're going to take care of, we're going to take care of the plus and minus signs logically. We don't have to rely on a calculator to do that. So 6 microcoulombs times 2 microcoulombs, and we have to change the distance too. So this is an equilateral triangle. And so if I do 10 squared plus 10 squared, that's going to be 2 times 10 squared. Then I take the square root of that, and that's going to be the square root of 2 times 10. So, which is 1.414. So then my denominator is going to be 0.14 squared. I got an extra decimal in there. Okay, that works. I have an extra power of 10 too. Whoops. So we'll delete that as well. No bother. Yeah, I don't like that. Well, let's do that one more time. So alpha K times, and we have 6 microcoulombs times 2 microcoulombs divided by 0.14 squared. There we go. Now, I'll just do this lightly. So I know that my angle here is going to be 45 degrees. because it's an isosceles right triangle. So I'm just kind of lightly here in pencil, I'm just going to write down. So we want to do 5.5 and cosine of 45, but it's along the negative x-axis. So I need to put a minus sign in there. And then for the y component, that's going to be positive 5.5 sine 45. So just kind of doing that really lightly. Now I can go ahead and do the math. So times cosine of 45. And so 3.9. So this result is going to be negative 3.9. And again, I'm putting the minus sign in here, not my calculator, because I know that this is pulling backward on it. It's going to help cancel some of this. And cosine 45 and sine 45 are the same number. So this pulls up with a force of 3.9 newtons. And now we can look at our total. Right, so I want to do 7.2 minus 3.9 just to make sure everything works out. So that's 3.3 newtons, and this is 3.9 newtons. And those are the x and y components for the answer. So the net force is going to have a magnitude that's equal to 3.3 squared plus 3.9 squared. And then we take the square root of the whole thing. All right, so square root 3.3 squared plus 3.9 squared. And for, yeah, that's good. 5.1, that sounds about right. And then the angle is going to be inverse tangent of y or x. So 3.9 over 3.3. So inverse tangent, make sure you're in degree mode for this. 3.9 divided by 3.3. Okay, and I get 50 degrees. Great. Now, so in general, the way I encourage people to handle the vector situation is that vectors can be described in two ways. These are two-dimensional vectors, so you need two pieces of information. The piece of information that humans usually deal with is what we call magnitude and direction. That's what I found here. This is the magnitude, and this is the direction. I should also be clear about this direction. I should make an indication that this is going to be sort of up and to the left, or actually it's going to be this way, right? So this is above positive x. So if we have magnitude and direction and we're trying to get into x and y components, then we should represent that the x component is going to be found with a cosine. So just kind of stylized here, Vx equals V cosine theta, where V is just some kind of random vector, and Vy is equal to V sine theta. But if we wanted to go the other way, like we just did, we had the x and y components for our sum, and we're going to go this way, then the magnitude of the vector is going to be equal to take the x part and square it, and take the y part and square it, and then take the square root of the whole thing. And then the angle is going to be equal to inverse tangent of the y part over the x part. So we actually did both of those here. We had a vector here that we wanted to add, but we can't add magnitude and direction. We have to add x and y components. So very lightly in pencil, you can see where I did this, applied cosine and sine to do that. Didn't need to do it here because this vector was along the positive x-axis, and none of it points in the y direction. And then I can simply add them up to find out the x and y components. So after I went this way and I got x and y's, and I could add them to get the x and y components of the sum. And then I went backward to get magnitude and direction as an answer. Okay, so a little bit of a review about vectors in general in this one. And I hope that's useful for you.